Yeah.
Yeah. Hi, everyone. So I'm really happy to have Mary Wootters from Stanford University to present to us today. She's going to talk about new tricks for old codes, the regenerated code editions. And so, Mary, again, I'm really happy that you're here, and we're all ears to listen to what you have to tell us.
Great. Yeah, so thanks so much for the invitation. Very excited to speak on the Shannon channel. I guess, yeah, before I start, I just want to say, please do ask questions, because my understanding of how this works is that I'm just going to be talking to like my slides in front of an empty room, which means that I've got no feedback if you don't interrupt me with questions. So please do interrupt me with questions if ever anything is unclear. Okay, so with that in mind, let me see if I can figure out how to make the technology work to show the slides. Where are they? Screen share. Do this. Okay, now that's inevitable. Where are my slides? Okay, can everyone see the slides?
I can see it, yes.
Yeah.
Okay, great. All right, so I guess I'll get started. Yeah, so I'm going to be talking today about new tricks for old codes, regenerating codes edition. And I'm going to be talking about a bunch of work, my own and others, but that's the work which is my own is going to be joint with Venkat Guruswami, and also work that's joint with Burak, Bartan, and Jay Mardia, who are PhD students at Stanford, and Venkat's at CMU. Cool. Okay, so the point of this talk, right, so what is this talk about? So regenerating codes, which I will define shortly, are codes which admit low bandwidth repair of just a few failures in a motivated by distributed storage. And it turns out that codes we know and love, like Reed-Solomon codes in particular, are actually pretty good at this. And there's been a whole bunch of work over the past couple of years kind of exploring the extent to which our old favorites are good at being regenerating codes. And so the point of this talk is to give an overview of some recent work in this area and to highlight a couple of open problems. So that's the main theme. So in a little bit more detail, here's the outline. So I'm going to start just by introducing regenerating codes. What are they? Why might we care about them? And then I'm going to focus in on the special example of Reed-Solomon codes in particular and talk about Reed-Solomon codes as regenerating codes, and also more generally what's called scalar MDS codes as regenerating codes. So these are just sort of MDS codes, sort of classical MDS codes as regenerating codes. And then I'll talk about a bunch of stuff, which I'm going to skip over in summarizing right now, and I'll conclude with some open questions. So that's the basic outline. So let's start with regenerating codes. So regenerating codes show up in the context of distributed storage. So the cartoon here is we've got some file, this guy. Can you all see the mouse if I wiggle this around?
Yes, we can
okay,
see
great.
you.
All right, so we've got some file, and we want to store it on a bunch of different servers or nodes. And the thing that's going to happen is that nodes might fail. So maybe they just go down for a little while. Maybe, I don't know, they catch on fire and the hard drive explodes. Maybe they're just too busy and being really slow, but for whatever reason, they can't be contacted right now. And we still want access to our data. So that's sort of the underlying problem that we're trying to solve. And slightly more precisely, in a more stylized way, here's the problem that we're going to be considering. So we're going to represent our file as k data blocks, so these blue guys. And we're going to want to encode these via an error-correcting code into n encoded blocks, so these guys here. And the idea is that we're then going to take each one of these encoded blocks and ship them off to a different server. So these yellow things are meant to be servers, just like they were in the previous slide. And so now if a server fails or a couple of servers fail, what we're going to think of in our model is a couple of encoded blocks have failed. And our goal is to try to somehow recover the data, even given failures of a couple of encoded blocks. OK, so that's the basic framework. All right, so what are our goals in this framework? So we have a couple of goals. So sort of the 0th order goal is we don't want to lose data. So what this means is we want sort of optimal robustness to worst case failures. And I'll clarify that a little bit more on the next slide. Goal 1 is that we want efficient repair of typical failures. So even though we will want to be able to sort of repair worst case failures, like the nastiest things that could possibly happen, we want to be able to handle those. For sort of everyday run-of-the-mill failures, we want to be much more efficient. This is all very vague. I'll make it more precise on the next slide. Okay, so what do I mean by these two goals? So goal 0, optimal robustness to worst case errors, or that should be failures. What I mean by this is the MDS property. So MDS, if you haven't seen it before, stands for maximum distance separable. This is just a property of a code. And by code here, I just mean some way of turning my k data blocks into my n encoded blocks. And what MDS means is that any k encoded blocks should be able to recover all of the data. So in particular, any n minus k failures can be tolerated. Right, so if I lose n minus k failures, I still have k encoded blocks left. I can still recover all of my k data blocks. And if you think about this, this is a very strong property because clearly we need k encoded blocks to recover all k data blocks just by counting. And this is saying that any k data blocks should do. So this is kind of the best case robustness to failures. And it turns out we can achieve this. We know of lots of codes which can achieve this. And so given that we can achieve this very strong notion of worst case robustness, we want it. So that's goal 0, is that we're going to demand that we have the MDS property. Goal 1, which I kind of waved my hands at before, is that we're going to want to be able to efficiently repair typical failures. So to define this a little more precisely, I need to tell you what I mean by efficient and what I mean by typical. So what I mean by efficient is going to be communication, and what I mean by typical is not too many. So to sort of give an example, suppose that only one node or one encoded block fails. We said that, okay, we want to be able to handle n minus k blocks failing, but it turns out that most of the time, maybe a typical failure is not too many blocks fail at a time, so maybe just one. And if just one thing fails, then we're going to want to be able to repair it, sort of set up a replacement node extremely efficiently. And again, what I mean by efficiency here is communication. So the amount of data that this new replacement node has to download from the other surviving nodes should be not too big. So there are plenty of different reasonable definitions of efficiency and typical here, and this is only one possible one, but I'd refer you to this really nice paper by Rashmi et al., where they sort of studied what goes on in the Facebook warehouse cluster, and they sort of documented that these are very reasonable definitions of efficiency and typical. So they showed in that case, communication, sort of network bandwidth really was the bottleneck in this distributed storage system. And also they showed that 98% of the time, basically only one node was failing at a time. So this is sort of a reasonable notion of efficiency and typical. Okay, so those are going to be our goals. We're going to want the MDS property. That's what optimal robustness means to worst case failures. And we're going to want low bandwidth repair of just a few failed nodes in the case that just one or two nodes fails. Great. I feel awkward now because at this point I would like pause and look at the audience and say, everyone with me? Does this make sense? So I don't know if internet audience, everyone good?
To me, so.
Sorry?
It makes perfect sense to me.
Fabulous. Okay. I guess that'll be good enough. Okay. Yeah. So let's keep on going. So let's see if we can see an example of this. So here's an example question mark. How did classical MDS codes do here? So for example, Reed-Solomon codes. So I'm going to define these more later, but for now, this is just an MDS code like we defined on the previous slide. So I have k data blocks, they get encoded into n encoded blocks, and it has the property that any k encoded blocks can recover all of the data. And here I'm going to think of each block as living in some finite field of size 2 to the t. So if you haven't seen finite fields before, no worries. A finite field is basically just some finite set where you can add, multiply, divide, subtract, sort of all the normal arithmetic operations you want, just as you could with integers, just as you could with real numbers. For the purposes of this talk, I'm always going to be working over a finite field of characteristic 2, meaning size 2 to the t. So I can think of any field element that I talk about as just being basically a vector of t bits. It's just that because it's in a finite field, I get to multiply 2 vectors and I somehow get out another vector, or I can choose to divide 2 vectors and I somehow get out of another vector. I sort of have that algebraic structure going on. Okay, so returning to the question at hand, how well do classical MDS codes do at this sort of distributed storage problem? Okay, so they are MDS. So that's goal 0 is satisfied. How about goal 1? So suppose that just one node fails, and I want to recover it. OK, so one thing I could do is the following. So any k blocks will recover all the data, and in particular, they'll recover the missing block. But this is actually not a great solution. This is very expensive. Right? I'm downloading kt bits of information. I contact k different blocks, and I download t bits from each of them, because I'm thinking of each block as having t bits in it. And this is actually enough information to recover the entire file. So basically what I'm doing in this process is I'm recovering all of the data, throwing out most of it, and just keeping the one block that I wanted. So it's very natural to ask if we can do better. So the first thing we might try to do is contact fewer nodes. So suppose we still have an MDS code, so same picture. One node fails. Now let's try to contact k-1 nodes instead of k. It turns out that this is also not a very good idea, because just any k-1 blocks here actually tell you nothing at all about the missing block, like literally nothing at all. And the reason is that this follows pretty much immediately from the MDS property. So any k blocks are enough to completely recover the whole file. So in particular, so here I have k-1 blocks, all these guys I'm downloading, and here's the kth. The missing one is like the kth block. And basically, the MDS property says that this kth block could be whatever it wants, and there's some legit file that corresponds to these k blocks that I've viewed. So that means that I really can't learn anything about this missing block with only k-1. OK, so try 1 does not work. So our next try, which is what we're going to end up doing, is to kind of counterintuitively contact more nodes rather than fewer nodes. But the catch is that we're going to download less information from each. And these are called regenerating codes. So once again, we have the same picture, k data blocks encoded into n encoded blocks, still an MDS code. But now, instead of thinking about these blocks as kind of indivisible elements of size, indivisible elements of a field of size 2 to the t, I'm just going to think about them as t bits, right? So I can manipulate them on the bit level. I don't have to think about them on the field level. And now what happens is if one node fails, I could try to replace it by maybe contacting more blocks, maybe all the surviving blocks, but I'll download less information from each of them. So maybe I'll download only 1 bit, for example, from each of them. And on net, I would hope to download less information than I was doing before. And it turns out that this way we actually can get away with less communication, which is pretty cool. So let me show you a real example now. So the first slide I showed you with the Reed-Solomon code was example question mark. Here's example exclamation point. So this is a real example. So if you've seen any talk on regenerating codes before, you have seen this example. But if you haven't, then you probably haven't seen this example, and it's a good example. So I'm going to go through it. So here's my example. I have 2 data blocks. And I'm going to think of each of them as a vector of 2 bits. So my first data block has x1 and x2. And my second data block has y1 and y2. And I'm going to encode these into 4 encoded blocks, again, each of which is storing 2 bits. So my first 2 blocks are just the same as my data blocks. And then I have these 2 parity blocks where I've kind of munged up the symbols x1, y1, x2, y2, like so. Okay. So I claim that this is still an MDS code, just to give an example. So I need to show that it can recover from any 2 failures. So proof by examples. Let's show that it works from these 2 failures. So if these 2 nodes fail and I want to recover the data, OK, so y1 and y2 are just sitting there. So I can download y1 and y2 and do that. And if I want to recover x1 and x2, I can do it like this. For example, x2 is equal to y1, which I've downloaded from here, plus y1 plus y2, or y1 plus x2, which I can download from here. And here all addition is mod 2. And so I can recover all the data. But note that this requires downloading 4 bits of information, which it should, because I'm trying to recover 4 bits of information. So far that checks out. But suppose now that instead of trying to recover all of the data, I want to recover just 1 node, right? So naively, I can still use 4 bits. I can do exactly the same thing I did before. Just to recover x1 and x2, this uses 4 bits. But actually, in this example, I can get away with downloading just 3 bits. And here's how. So instead of contacting only 2 other nodes, I'll actually take advantage of the fact that that 3rd node is still alive and contact it as well, and download just 1 bit from each node. And when I do this, I can get, for example, x2 is equal to y2 plus x2 plus y2, again, mod 2. But x1 is equal to x2 plus y2 plus x1 plus x2 plus y2, mod 2. And so I can get it from these two things as well. Right, so now I've recovered all of the lost information, x1 and x2, using only 3 bits instead of 4. So this is better. And we can do this for any node that fails. So for example, if this parity block fails, then I can recover it. I have to be a little bit more sneaky, though. So here I can still recover it using only 3 bits, but now I'm going to allow this node here to do some local computation. So instead of sending either y1 or y2, which are the 2 bits that it's holding, it's going to add them together and send the sum. And then it turns out if you allow them to do this, then this system can be repaired. Any block can be repaired using only 3 bits of communication. And again, nodes are allowed to do some local computation. OK, so that's regenerating codes. So regenerating codes allow for low bandwidth repair of a single or a few failed nodes while maintaining the MDS property. So they were introduced, I guess, 8 years ago now by Demakis et al. Or this was one of the first papers that kind of set things going. And since then, there has been tons of work, both in theory and practice. And so this is just a random sampling of things I could possibly have cited here. So it's really a rich area of work. Actually, before I go on, are there any questions about the example that I just gave, or the goal of regenerating codes?
I think the example was clear.
OK, great.
I was even discussing asking it because I teach this. Oh, I should not say this. I'll tell you offline. OK, sounds good. Right. OK, so regenerating codes have been around for 8 to 10 years or so. There's been tons of work on them. And with all this work comes a whole bunch of different parameters we might care about and a whole bunch of different things we might try to optimize. For this talk, I'm just going to try to focus in on just a few different parameters we might care about to avoid kind of drowning in parameter soup. So here are a couple of parameters that I'm going to care about for this talk, again, with the caveat that there are plenty of other things that one might care about. OK, so the first thing I'm going to care about is the bandwidth. So how much data is actually downloaded to do a repair. Right, so in the previous example, that was 3 bits to do a single repair. The second thing I might care about is the subpacketization. So how many subsymbols live in each node symbol. So in the previous example, there were like 2 bits per node. So the subpacketization would be 2. So more generally, I can take my big node and I can break it up into however many symbols I want. And for this talk, the thing that's relevant about the subpacketization is that the size of the small symbols here are sort of the smallest unit that I can work with. So if I'm sending these subsymbols, I can't break up the subsymbols any further. This is the smallest I can break them up. So for this talk, it's the size of the subsymbols are mostly just going to be bits. Right, and so smaller subpacketization is better in general. Another thing one might care about, which I'm not going to care about too much for this talk, is how many nodes are actually contacted. So in this talk, I'm going to say you're allowed to talk to any node that is still alive. It is also interesting to ask what happens if I'm only allowed to talk to, say, like k+3 nodes, even if many more are available. But I'm not going to talk about that. Another thing one might be interested in that I'm not going to talk about is how big are the encoded blocks compared to the data blocks. So in all my examples and pictures so far, I've kind of had the data blocks and the encoded blocks about the same size, and they're supposed to be like the same type of thing. And I'm going to continue with that for the rest of the talk. However, I just want to mention this can be relaxed. But for this talk, encoded blocks and data blocks are all the same size. They are all finite field elements of finite fields of size 2 to the t. That's what we're going to be working with. OK, so once again, the main parameters we're going to be caring about are the bandwidth and the subpacketization. And the goals that we have are, first, the MDS property should hold. Second, the bandwidth should be small. Third, the subpacketization should be small. And fourth, I didn't mention this on the previous slide, but the size of the subsymbols should be small. Because if the subpacketization is small, but the size of the subsymbols is really big, that is kind of cheating. We're not actually getting away with less bandwidth measured in bits there. So for this talk, we should think about these subsymbols are always just 1 bit, and the subpacketization is just the number of bits per node. And we want that to be small.
Another thing we're going to mention a little bit in this talk is we're going to want to be able to handle multiple failures. So I sort of motivated it in the case of one failure, but it's nice if it can sort of gracefully degrade as the number of failures increases. And one thing I'm not going to talk about in this talk, but which I think is interesting, so I'm just going to mention it, is that it's nice if each node should not access too many subsymbols when it participates in a repair. So I've said that it should send as few symbols as possible. But for example, if it's allowed to do some local computation, then nothing is preventing it from like looking at everything on the whole node and maybe even doing some terrible computation and then sending the single bit. We'd like to make things easier for the individual nodes. That said, I'm not going to talk about that in this talk too much. Just want to mention it. Cool. OK, so that's regenerating codes. And so that was sort of the first part of the talk, is high-level intro to regenerating codes and the parameters that we're going to care about. So the next part of the talk is sort of looking at codes we know and love functioning as regenerating codes. So let's go into that. So far, we have seen exactly one example of a regenerating code, which is this k equals 2, n equals 4 example. And that example was something called an array code. And most constructions of regenerating codes in this big, rich literature are array codes. And what I mean by that is that each symbol of a code word, so each sort of encoded symbol, is naturally thought of as a vector over some smaller field. So for example, here we have some code word. This guy's meant to be my encoded blocks. The first symbol, x1, I would naturally think about it as actually a vector of length t over some field b. B stands for base, like the base field. And then the code, which I think of each code word now as kind of being an array that looks like this, is linear over the small field, but it's not a linear code to begin with because its alphabet size, its alphabet is not actually a field, it's a vector space. And so most constructions are array codes and kind of look like the toy construction that we saw before, where we're kind of very carefully designing what symbols go in which nodes so that they play nicely together so that we can recover things. This looks very different from sort of classical codes, especially classical algebraic codes that we know and love. And so this talk is about the MDS codes we know and love. And the motivating example is Reed-Solomon codes. So if you haven't seen Reed-Solomon codes before, let me quickly define them. So a Reed-Solomon code, like I said before, it's an MDS code. So it has this property that any k encoded blocks can recover all of the data. And it's defined as follows. So suppose I have my k data blocks, and I'm going to name them f0 through fk minus 1. And then I'm going to treat these data blocks as coefficients in a polynomial. So I'm going to let f of x be this polynomial f0 plus f1x plus dot 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 plus fk minus 1x to the k minus 1. So some k minus 1 degree polynomial. And then the way I'm going to generate my encoded blocks is I'm going to pick n different evaluation points, alpha 1 through alpha n. And I'm going to evaluate this polynomial f on each of these different evaluation points. And this is going to give me now a code word of length n. And so here, the symbols very naturally are elements of some finite field. Again, for this talk, fields always have size 2 to the t. And the encoded symbols also very naturally live in this big finite field. So that's the definition of Reed-Solomon codes. And so these look pretty different from the array codes we saw on the previous slide. So two major differences are that the symbols live in a big finite field instead of something that is explicitly a vector space. And also the code is linear over this big finite field, whereas the previous code was linear, or like array codes are linear over smaller fields, but they don't have the same algebraic structure. And so codes like this sort of that are linear over a big field and sort of naturally live over a big field are called scalar MDS codes in the regenerating codes literature. They're sort of what we would just normally call straight up MDS codes, but we call them scalar MDS codes to differentiate them from MDS array codes, which is the thing we said before. OK. And so this talk is about understanding sort of to what extent sort of scalar MDS codes like Reed-Solomon codes can be used as regenerating codes, because sort of on the face of it, it's not clear if we can't like start mucking with the subsymbols or designing the subsymbols in particular ways. Like how can we try to make this these sort of happy cancellations occur, like happened in the previous example, where I could sort of magically get away with just 3 bits. Right, so yeah, so that's what this talk is about, and in particular, it's about MDS codes we know and love. The motivating example is Reed-Solomon codes, and I would just want to briefly deviate from the narrative to point out that we do love Reed-Solomon codes, or I love Reed-Solomon codes. They're my personal favorite code. But they're actually used in distributed storage. For example, the Hadoop distributed file system has a module which allows for Reed-Solomon codes. And they're also all over the place, not just in distributed storage. They're on hard drives and CDs, spacecraft, QR codes. Really, they're completely ubiquitous. So Reed-Solomon codes are codes that we know and love. OK, and so now that we know that we love Reed-Solomon codes, let's try to understand this repair problem for Reed-Solomon codes in particular. So here's what the problem looks like. So I'm just taking exactly the same problem we had before. I'm just now writing polynomial evaluations on top of it. Right? So suppose we have some Reed-Solomon code word. So that is, we have some low degree polynomial over some finite field. We have a bunch of evaluation points. Here's our code word. Now what's going to happen is some node is going to fail, like this one. So we've lost an evaluation point, and we'd like to repair it. So we would like to repair this node, so we'd like to recover this evaluation point. And the way we're going to do it is by downloading some information from the surviving nodes, aka the surviving evaluation points. And the rules are what is sent from, for example, node 1, this guy, can only depend on its contents, f of alpha 1, and the identity of the failed node. And our goal, again, is to minimize bandwidth. So this is the problem for Reed-Solomon codes. And I'd just like to point out that I think this is a really neat problem, completely independent of the storage motivations, just as a problem about polynomial interpolation. This seems like a pretty natural, cool problem. So I like thinking about it for that reason. Great. OK, so now we've talked about regenerating codes. I've kind of motivated, like,
a small question. So because you're saying it's an interesting problem by itself, have you seen it like arise from in other applications, or?
Yeah. That is a great question. That is one of my open questions at the end. Actually, is that Reed-Solomon codes appear just all over the place. I feel like this polynomial interpolation question ought to appear somewhere. And I'd be really curious if you or anyone else who's listening has any ideas. One area that it seems like it might be very relevant is in secret sharing.
Yeah, exactly. That's what I had in mind.
Yeah. So I mean, I'd love to talk more later about applications of this in secret sharing. It seems like that might be that might be a very fruitful area. Yeah. Cool. And I have some ideas along those lines that I'd be happy to chat with you about offline.
Sure.
Great. Cool. OK, going forward. So we talked about regenerating codes. We talked about codes we know and love, or like why we might want to study sort of classical codes as regenerating codes. And so now I'm going to sort of focus in on the technical meat of the talk. That was kind of the big introduction. And sort of focus in on this little sub-outline. So what I'm going to do for basically most of the rest of the talk is sort of first focus in on the single failure case. So what happens if there's just one failure? There's actually been a fair amount of work on this, so I'll kind of tell you the story so far. And one punchline is going to be that for scalar MDS codes, you can actually completely characterize a certain class of repair schemes based on just some nice algebraic property of the dual code. So I'll sort of tell you the framework for characterizing this, and then I'll give you one construction that lies in that framework for answering this polynomial interpolation question for Reed-Solomon codes. And then time permitting, I'm going to move on to talking about multiple failures and show how to scale, or how to extend this framework from the singular failure case to the multiple failure case, and give one more construction that works a little bit better for multiple failures. Cool. OK, so that's the plan. So let's get started with the story so far for Reed-Solomon codes. So there's actually been a fair amount of work on this. So the question, to best of my knowledge, was first raised by Demakis et al. In 2009 or 2010, somewhere around there. But the first work on it, sort of making progress on it, wasn't until just a couple of years ago with this work of Shanmugam et al. In 2015. And what they did is a really nice paper. They showed that actually there exist Reed-Solomon codes of length, to particular Reed-Solomon codes like of length 5 or length 6, which admit non-trivial repair schemes. And when I saw this paper, it basically just blew my mind, because I have been raised to believe that you need k evaluation points to learn anything about a degree k-1 polynomial, or anything about an additional evaluation point of a degree k-1 polynomial. And so I thought it was crazy that you could do better information theoretically. So this is just a really nice paper. And so that started me thinking about it. And yeah, since then, there's been a fair amount of work over the past few years, most of it focusing on the single failure case, but then a couple of works in the past few years focusing on the multiple failure case. So let me kind of sort of summarize what's known. So to summarize what's known, I need to sort of break things up into two different parameter regimes. So again, I'm just going to start out thinking about a single failure. And the two parameter regimes have to do with the level of subpacketization. So we should think about this as how many bits per node. So when the subpacketization is very large, so here large, think like exponentially large, like really large, then the sort of right thing to shoot for in terms of what is the best bandwidth we can get is something called the cut set bound. So the cut set bound, which was proved by Demux et al. In 2010, says that for any scheme, not just for Reed-Solomon codes, not just for scalar MDS codes, but for any regenerating code, the total bandwidth you need has to be at least t times log base 2 of b times n-1 over n-k bits. I should say this is usually stated without this log base 2 of b, and it's measured in symbols of b. I'm just going to measure it in bits so that everything is in the same units, which is why I grew this extra log factor. But I should say this bound is really remarkable because, or it's remarkable if we can achieve it, because like how many bits are we trying to recover? Well, we're trying to recover one symbol of our code, which has t subsymbols, each of which take log t bits. So we're trying to discover, or log of b bits. So we're trying to recover this many t times log base 2 of b bits total. And this is saying that with a constant rate code, you only need to pay like a constant factor overhead on that. And the awesome thing is that this is achievable. And the awesome thing for the story about Reed-Solomon codes is that actually this is achievable with Reed-Solomon codes. So this is a beautiful result of Tomo, Ye, and Barg from last year, where they actually show that Reed-Solomon codes can achieve this. However, sort of on this side of the screen, this large subpacketization side, this large t that you have, this really, really big t, is necessary. So Tomo, Ye, and Barg actually showed that for any scalar MDS code with a linear repair scheme, you need t to be at least exponential. And even in general, if you don't want a scalar MDS code, you do need t to be large, at least polynomial in n. And that's not very helpful. The degree, like the exponent on the polynomial should be like at least 2 or something. So it's solidly bigger than n.
So how about the result of your third bullet that says that RS codes achieve this? Are there bounds on Q on the field size?
The field size in this work is quite large.
Okay.
And so again, the field size is something to the t, and t itself is exponential in k. So the field size is going to be doubly exponential in k. Okay. And unfortunately, that's necessary if you want to meet the cut set bound. Does that make sense?
Yep.
Yep. Yeah. So that's yeah. So those are sort of the trade-offs of the things that happen on this side of the screen. Like the good thing is that we can meet the cut set bound, which is this really tight bound, sort of as best you can do, that says you only really have to have this constant factor overhead if you have a constant rate code. The downside is that you need enormous field sizes. And so motivated by that, one might try to look at the small subpacketization regime. So here, let's think of t as being like logarithmic in n. So this is sort of the natural setting for example, Reed-Solomon codes, where I would have n, the length of the code, being the size of the field. Every single evaluation point shows up. There are 2 to the t evaluation points. So n equals 2 to the t. So t equals log n. So that's sort of the natural parameter regime for Reed-Solomon codes, or for full-length Reed-Solomon codes. The way you make t much, much, much bigger is by looking at much, much, much smaller sets of evaluation points. But in this small subpacketization regime, think that we're taking the whole field as evaluation points, and t is like log n. So in this setting, the cut set bound just can't be achieved. It's impossible. But what we do know is that Reed-Solomon codes can achieve bandwidth something like this. And I'll sort of show a cartoon explaining why this is a reasonable number in the future, or like on a future slide. But basically, this is saying that you can download basically a constant number of bits from every surviving node if only one node fails. And moreover, this is optimal for scalar MDS codes with linear repair schemes. That's what the asterisk means, is with linear repair schemes. And that's for scalar MDS codes, it's optimal for. In general, if I don't want to look at scalar MDS codes, or if I don't necessarily want to restrict myself to linear repair schemes, whatever that means, it's known that in this parameter regime with small subpacketization, the bandwidth needs to be at least k plus t minus 1. But in general, this parameter regime is much less well understood. We don't really know what's possible. And the takeaway that I guess we should take from all of the parameters on this slide is that in the large subpacketization regime, what's happening is that the bottleneck on the bandwidth is t, right? Basically, we want to download t bits, and if t is really big, then t is the bottleneck because we need t bits, so that's really big. On the other hand, in the small subpacketization regime, the bottleneck is k. With any MDS code, we're going to need to contact at least k nodes to learn anything, and so if k is much bigger than t, then k is the bottleneck. And so these are sort of the two different parameter regimes, one where the bottleneck is t, one where the bottleneck is k. And for the rest of this talk, well, I'm going to talk about a framework that works in both of these parameter regimes, but I'll explain a little bit how to get this result for small subpacketization, where the bottleneck is k.
For the result you're circling, so are you contacting all n-1 nodes?
That's right. Yeah. So you contact the n-1 surviving nodes, and you download sort of this many bits from each. So in particular, if k is like n/2, you're downloading just one bit from each surviving node.
Okay.
If you want to contact fewer nodes, you can do that as well, and I'll get to that at the end of the talk.
And how does this compare if it's to the optimal information theoretic bound?
This match. So this is optimal for scalar MDS codes for linear repair schemes. So this is optimal within a class of codes, within a class of schemes. It's I guess the best information theoretic bound we know in general in this parameter regime is this one, k plus t minus 1. And so here, think of this bound, if k is like n/2, as being about twice this information theoretic optimal bound.
So you don't allow to divide the symbols here?
Correct. Or we are allowed to divide the symbols into bits, actually. Yeah. So we're not allowed to subdivide bits any further, but we're allowed to.
No more than log of, and no more than t.
Exactly. Yes. T is the subpacketization. So that's sort of definitionally the number of sub-symbols we're allowed. That's right.
Okay.
Yeah. Cool. Yeah. So once again, yeah. So this result is optimal for scalar MDS codes, and whether it's optimal for all codes, we don't know. We don't have any better constructions, but it's about a factor of 2 off of the lower bound, for example, for rate 1/2 codes. Great. Okay. So how should we begin to think about repair schemes for scalar MDS codes? Right, when we saw that sort of example, that 2-bit example at the beginning, it seemed very crucial that we had kind of this array structure because it allowed us to kind of put particular bits where we wanted. And now we're just handed these MDS codes which have this structure over this finite field, and how do we look inside? So before we even start thinking about how to do this, we should answer a few questions. So question 1 is like, what should a node send? What is a reasonable thing for a node to send? Right. So each node here is an element over some big finite field, but it's going to be returning a bit or a couple of bits. If it can do anything it wants, like how should we possibly narrow this down? What could it do? And then the other question we need to answer is how can we take advantage of this sort of linear MDS structure? So if I have a Reed-Solomon code, this has a lot of algebraic structure, and I'm going to want to take advantage of that somehow. So those are sort of 2 leading questions. And the answer to both of them turns out to be linear algebra. So sort of motivated by these 2 kind of vague questions, let me take a brief detour into linear algebra. Okay, so the first linear algebra thing that we're going to need is field traces. So suppose we have some subfield B which is a subfield of F, so that F has degree T over B. So once again, just think of F as being F2 to the T, finite field with 2 to the T elements, and B, our base field, is just F2. And T is our level of subpacketization. So every node holds an element of F, which is just T bits, and we're allowed to return bits. So it turns out that F is actually a vector space over B of dimension T, whenever you have this. So that means, which I kind of said before, that any element of the finite field I can sort of naturally think of as a vector of zeros and ones, or of elements of B more generally. So a vector of length T. And for the rest of this talk, I'm going to draw square things to mean elements of my big finite field, and these sort of long skinny things to mean the vector version of it, if I think of it as a vector over B. And so the field structure gives us all sorts of nice operations that we can do on these vectors, right? We can add and subtract them, which we could always do, but now we can also, for example, multiply 2 vectors, get another vector out, divide 2 vectors by each other, get another vector out. Kind of cool. One additional thing that we like to do with vectors that we would like to do in this case is take inner products. So we'd like to take the inner product of 2 of these vectors and get out an element of B, the small field. And turns out there's some nice algebraic machinery to do that too. It's called the field trace. So B linear maps from F, the big field, down to B, the small field, are completely captured by the field trace. So that is, if I have my element of my big finite field, f of alpha 1 here, and I'm thinking of it as a vector here of length t, then if I want to consider the inner product of this vector of length t with some other vector of length t, which is going to spit out some scalar in B, the small field, so think of this as just a bit, then I can do this sort of over the big finite field by taking a trace. So trace, which is some operation that I'm not going to define, is something that takes in an element of the big field and spits out an element of the small field. And what this cartoon is meant to imply, the true fact, is that if I take the trace of the product of 2 elements over the big field, what comes out is a single element over the small field, which I should think of as being the inner product of the vector versions of these 2 things. And it turns out that basically everything you want to be true about inner products is true about this operation. So going forward, I'm just going to sort of use this operation and inner products interchangeably. And this kind of starts to answer our first question of what should nodes return. I'm going to focus on schemes where a node J returns the trace of some field element, gamma, times what it's holding, which is, in this case, for Reed-Solomon code, f of alpha j. So what this is saying is that if I take that node, which is holding this field element, and I treat it as holding a vector, then I'm going to allow it to return sort of any linear thing it wants to do with that vector. So just like a dot product. Make sense?
Yes.
Good. Cool.
So basically, trace are inner product.
Sorry?
So basically, trace is an inner product. I mean, this is the...
Yeah, that's basically what you should think about it as. Yeah, so it captures, so basically any B linear map from F to B looks like this somehow. Just the same way that over a vector space, any linear map from the big vector space down to the base field looks like this somehow. So there.
Is it related to trace of matrices, or it's totally different?
It is, yeah. So if you...
Oh, maybe...
If you write this guy as a vector, so this field element I treat as a vector, and then if I multiply these 2 field elements, that's some linear operation over the small field. So that corresponds to multiplying this vector by some matrix over B. And the trace of gamma ends up being the trace of that matrix. Yeah, so
So I have a question also.
Yeah.
So the inner product in general is about the space and the dual of the space. Is there some duality here also? Is this gamma like... you understand what I mean?
Yeah, yeah, that's right. So you're saying that in a vector space, the sort of I can think about the set of all linear maps from the vector space down to the base field.
Exactly.
That itself is a space, which is the dual. Yeah,
and that's the general definition of the inner product. And then it has nice properties, and in the finite case, it's Good. And I mean, does this trace operation have the same type of dual notion, or do you know?
Yeah, so it's basically the same sort of thing is going on. So in the same way that if I were to look at all of the sets, if I were to look at all of the linear functionals from a vector space down to the base field, and I get a set of vectors or in the finite dimensional case, the same way here over a finite field, if I look at the set of bilinear functionals from the big field down to the small field, they all look like this: trace of something times your argument.
So it is an inner product, and like in
yes,
a sense.
Yes, exactly. In that sense, that it's exactly the same.
It is an inner product. Okay.
Or there's.
Well, why don't you just call it an inner? This is what I want to understand. Why equivalent? Why not? It is.
Oh, because it has other algebraic properties as well,
okay.
Which make it somewhat nicer than just an inner product, which we'll see on future slides. We'll see a couple of nice properties of
okay.
the trace.
Thank you.
Yeah, so it acts as an inner product when I treat these things as vector spaces. It also plays really nice with the multiplicative structure of the big field, which doesn't play a role in the vector space structure. Does that make sense?
Yes. Thank you very much.
Cool. Yeah. Great. Okay, so speaking of duality, although now this is a different notion of duality in a different space, the second piece of linear algebra we're going to need is dual codes. So suppose that I have a code which is a linear MDS code over some finite field. So for example, a Reed-Solomon code like this one. Then we define the dual code to be the set of all code words whose inner product, or sorry, the set of all vectors over f to the n whose inner product with all of the code words is 0. And for Reed-Solomon codes, fun fact, the dual of a Reed-Solomon code is actually again a Reed-Solomon code, or technically a generalized Reed-Solomon code. I'm just going to ignore that. Which means that if I look at any sort of low-degree polynomial f and any low-degree polynomial g, where the definitions of low degree are complementary in this way, then the inner products of these two vectors is 0 over the big field. Okay, so that's the second thing we're going to need, and this is going to be sort of the linear structure over the big field that we're going to take advantage of. Cool. And so the characterization that I'm going towards here is this one from the joint work of myself with Venkat Guruswami, which showed up in IEEE Transactions of Information Theory last year. And the statement is the following. Okay, this is not a formal statement, but the informal statement is the following. If you want a nice bilinear repair scheme for some scalar MDS code C, that is equivalent to coming up with a nice property of the dual code. And I'll tell you what nice property means in a second. And the corollary for Reed-Solomon codes is that nice linear repair schemes for Reed-Solomon codes, okay, so those correspond to nice properties of the dual codes. Dual codes of Reed-Solomon codes are again Reed-Solomon codes, and Reed-Solomon codes are just low-degree polynomials. So that translates into nice properties of low-degree polynomials. And so the way we get sort of the advertised repair schemes for Reed-Solomon codes is by coming up with nice families of low-degree polynomials. So this is sort of the characterization. So let me tell you what I mean by a nice property. So here's the nice property of the dual code that we'll be after. So the property is as follows. I'm going to sort of define it by picture. So for every I, which is a possible symbol that might have been erased, so think of I as being the failed node, I demand that there exist a set of dual code words C1 through CT. So here they are. I've written them as the columns. So that the following holds. If I look at the ith row, this is the one that corresponds to the failed node, then these symbols here that show up in this ith row should be full rank over the small field. And I'll say a bit more about what that means in a second. And if I look at any other row other than the ith one, then these symbols should be low rank. So what does that mean? So I just said that elements over my big field I should think of as vectors over my small field. And so when I say full rank, all I mean is that the t elements over the big field, I can think of these as t vectors of length t over the small field, aka a t by t matrix, and I want this matrix to be full rank. And then similarly for all the other rows, I want the corresponding matrix to be low rank. And the claim is that if I have this nice property in my dual code, then I have a nice repair scheme.
Mary, are you saying that every dual code should show? So I'm a little bit confused. So the columns here are what is C1?
Yeah, so the quantifiers are for every I, there exists a set. So for every I can find some T dual code words.
Okay.
That have this property.
Oh, so that's a code word. I thought every column is what's stored on it. This is not true. So that's a.
Oh yeah. So these are dual code words. Yeah. So now, yeah, I've rotated them.
Okay. So you just take there existed T. There's a set of, and do we know what T is? Oh, T is your T. Is the subpactization, the number.
That's right. Yep. Same T.
Okay. So there's T of them. Oh, and then every square in orange is an element of the bigger field. So it's a matrix. I can look at it as a vector over the smaller field.
That's right. Yeah. So this square here I think of as an element of F. So I'm in this picture here. I've like turned that one square into this tall, skinny vector of length T over my small field B.
And this is true for any dual code of read someone, or I'm just trying to see if this is like a different way of a classical result in coding theory, or whether this is kind of like you want this property.
So this is the property that we want. I will show you how to get it.
Okay.
It's not obvious, but yeah. But first, before I show you how to get it, let me show you why it's useful.
Sure. Yeah.
Yeah. So why is this useful? So here's this nice property. I claim that it's equivalent to getting a nice repair scheme. I'm going to just show you this direction that it implies a nice repair scheme, and then the converse is basically just linear algebra and imposing enough assumptions in the definition of nice. But so here's basically how it's going to work. So suppose that node I fails, and for simplicity, I'm just going to say that I equals 1. Same thing works for any I. And let C1 through CT be these vectors that I am hypothesizing exist, because I'm assuming that my dual code has this nice property. So suppose that these C1, CT exist for this particular node I. So then I get a picture that looks like this. So here's my C1 through CT. The first symbol has full rank. All the other ones have low rank. So now what I'm going to do is consider taking the inner product over the big field now of each of these dual code words with the code word that I am trying to correct. So this is a thought experiment. I don't actually know what this code word is, but let's imagine we could do it anyway. So here's the code word that I actually have. So once again, each one of these symbols I think of as being shipped off to a different node, and the first one has failed. Okay. So now I can consider all of these different inner products. And because all of these guys live in the dual code, all of these inner products are 0. Okay. So far, nothing fancy. And the next slide, still nothing fancy. I'm just going to do some subtraction, right? So over here on this side, I have 0, T different zeros. And over here, I have a sum of a bunch of different things. So what I'm going to do is I'm just going to subtract all of the terms that correspond to the first symbol over to the other side. So there. So what's left is that I have this first symbol, which is this missing guy times those first full rank symbols of C1 through CT, let's call them gamma 1 through gamma T, minus that is equal to what's sort of left over here, which is the inner products of the symbols of these vectors if I just restrict them to the second through nth symbols. Is this clear? It's just subtraction, but the picture ended up being a little more confusing than I intended.
Yeah.
Okay, good. Okay, so yeah, just subtraction. Great, so now we have this equation. And so now what I'm going to do is I'm going to take the trace of both sides.
So, so you mean like instead of x1, you would have a 0, right?
Well, I don't know what's there. It's failed.
Oh, okay.
Right. So far, I'm not designing a scheme. I'm just telling you some true algebraic facts.
Okay.
And once we're done with the true algebraic facts, a scheme will kind of pop out.
Okay.
But so far, here's just some true fact. And now what I'm going to do to this true fact is I'm going to take the trace of both sides. Right, so what's on the left-hand side, I have T different symbols over the big field, each of these inner products. And on the right-hand side, I also have T elements over the big field, x1 times gamma 1, x1 times gamma 2, and so on. So I'm going to take the trace of each of these elements individually, like this. And now what I get is T bits let's say, are t elements of the small field. So here I have the trace of x with the first dual code word, ignoring the first symbol, and then the dot trace of x, inner product, the tth code word, and on the right, I just have the trace of all of these different products. Okay, so all I've done is take the trace and assert that these things are still equal. So now we can do the same thing that we wanted to do earlier, or the same thing that we said earlier, which is that trace here is essentially an inner product, or is acting like an inner product. So I should think of this bunch of bits here as being an inner product between x and like what happens when I treat gamma 1 as a vector, and then what happens if I treat gamma 2 as a vector, and so on until what happens as I treat gamma t as a vector. So what this bunch of bits here is just x1 treated as a binary vector times some full rank matrix over f2. And the full rankness is because that was my assumption in my definition of the nice property. Does this make sense?
Yes.
Good. OK, and now I'm going to do the same thing on the other side.
Did we use any property of trace here, or?
Just the fact that it's just the fact that I should think of it as a inner product.
Okay.
Yep. And once again, I can do the same thing on the other side. And again, I'm only using the fact that I can think of trace as an inner product, which means just that it's bilinear. So that's all I'm using is the bilinearity of the trace here. To write what's going on over here as something like this. The sum over j from 2 to n is coming from the fact that there are symbols here that go from 2 to n. And what shows up on the inside is the sum of a bunch of things where I have basically the same picture as I had over here. Xj is a vector times some matrix, which corresponds to the jth symbol in each one of these code words. But now the assumption is saying that instead of being full rank, this guy should be low rank. Right, so exactly the same. And so then what the correspondence here is saying, I said trace is the same as an inner product. So this equation implies this equation down here, except that I forgot a minus sign, but we're over characteristic 2, so it's OK. Sorry. Yeah, so imagine there's a minus sign here. And we end up with this equation down here, if we want to think about things as vectors. So I'm just going to move this equation over to the side. OK. And I claim that just by staring at this equation, this immediately gives us the repair scheme that we wanted. So here's the scheme. Looks like this. So I have my vector, or sorry, here's my code word with my missing node that I want to repair. I want to, here's the replacement node that I want to figure out what was on this contents. And then each surviving node needs to send something. So what's it going to send? Well, it's going to send exactly enough information to convey this thing. So that's itself as a vector, it knows that, times this low rank matrix. And this low rank matrix here, this just depends on the code. So this is public, everyone knows it ahead of time. The only thing that's private to this node is sort of its own contents. And the point is that because this matrix is low rank, this matrix vector product is just the element of some low dimensional subspace. So it's, let's say it's an element of some subspace of dimension R over B. So how many symbols do I need to send to tell you about element of a particular R-dimensional subspace? Just R symbols. So what this node is going to send is just R symbols from B. So if in the case when B is just F2, this is R bits. And so now this basically gives me the whole scheme. So every node is going to convey just these R bits. And you might even think of R as being 1. So like every node just sends 1 bit or something. And then what the receiver is going to do is go take a look at this equation that we just derived. Now it knows all of the things that go in the summands here. So now it can compute the left-hand side, or the top side. And then what it's computed is the thing it wants times some full rank matrix. So then it can just invert the full rank matrix and find the thing it wants, and then it's done. So that's the whole scheme, assuming we have this nice property. Does this make sense?
Yes.
Great. Cool. So I realize it's 11. How long am I supposed to be talking for?
How much time do you still need?
I could go for quite a bit more time, or I could wrap it up pretty soon. Which should I do?
I'm personally very interested. So So, so how much, like, if you need to, because I feel like this is getting to the meat of things, you know.
Okay,
and
cool.
People who want to watch it later on, you know, who are interested to know more, I think they would have time also to watch, I mean, slowly, or, you know, take their time. So if you have time to explain this more, I mean, we can. You know.
Okay, great. Yeah, I have time. Okay, yeah. So maybe I will. I'll have like a pseudo stopping place on the next slide in which everybody who's currently online who wants to leave can quietly turn off and go away, and I won't be offended. And then after that, I'll keep talking, and we can see.
Okay.
Okay, great. So here's the pseudo conclusion is that we have this nice property of dual code words is equivalent to a nice repair scheme. So I just showed you this direction. The other direction basically follows from linear algebra. So you can show that if you have a linear repair scheme, so all bilinear repair schemes basically look exactly like the one we just described. And this follows from the fact that someone was asking about earlier that all linear functionals from the big field to the small field look like trace. So you can show that all things look like this. So in fact, this is an equivalence. And the corollary for Reed-Solomon codes is that nice properties of low-degree polynomials are equivalent to nice repair schemes for Reed-Solomon codes. So we just want to come up with a bunch of dual code words, which is a bunch of low-degree polynomials that have this nice property. Unfortunately, we can find these nice low-degree polynomials. So all the sort of the previous work that I showed before, they all go by finding nice families of low-degree polynomials. Here, I'll flash them up again. So here's a bunch of different constructions, which are all sort of based on this framework, and which all find nice low-degree polynomials. So both in the small subpacketization regime, when the number of evaluation points is the whole thing, and also in the large subpacketization regime, when you take the number of evaluation points to be much, much, much smaller than the whole field, and they're chosen very carefully to have some nice algebraic structure. Okay, so I guess maybe here's the point at which those who need to go can exit. So here's the punchline, and we can find these low-degree polynomials, and everyone's happy. So for now, as long as people are willing to tolerate me talking, I guess I will say a little bit more about how we might actually come up with these. So I'll give you a construction of these polynomials. And so this is based, again, on this paper with Venkat Guruswami, and also is later refined by Dow and Milankovitch.
So one quick question. So when you talk about low-degree polynomials, isn't the degree of the dual code, like, isn't it imposed by because it's Reed-Solomon, right? So the dual has degree n minus k, right?
That's right. Yeah. So here, I mean, I'm saying that both degree k and degree n minus k counts as low degree in my book.
Okay.
But yeah. So maybe if we want high rate codes, we should say low-ish degree polynomials, not too low, which is good for us. Great. Okay, so nice low-degree polynomials. So I'm just this construction is actually more general, but I can just tell you an easy construction in this very restricted parameter regime. When the field, the evaluation points are the whole field. The field is f2 to the t. The rate is 1/2. So just take k equals n over 2. So then k is equal to n minus k, and I don't need to worry about it. Everything is low degree. And the base field is just f2, so bits. And once again, I want to come up with a bunch of dual code words, which in this case would just be polynomials of degree at most n over 2, which is n minus k, that have this property. So on one special evaluation point, which I'm just going to say is 0 for simplicity, these guys should have full rank. And on all the other evaluation points, they should have low rank. And in fact, they're going to have rank 1. So here's the construction. I'm just going to kind of pull it out of a hat. So suppose that gamma 1 through gamma t is a basis for f over b. So remember, f is a vector space over b, so it has a basis. So gamma 1 through gamma t can be that basis. And then I'm going to define my polynomials. So these are going to be polynomials, which I'm going to think of as code words in the dual code. Here they are. I'm just completely pulling them out of a hat, but this turns out to work. So what is this? Okay, so I'm defining g sub I of x to be this thing. This is the trace, the same trace that we had before. Now this is where the fact that it plays nice with the sort of big field structure comes into play. The trace of gamma I times x divided by x. So I didn't tell you what the trace was, but it turns out it's just some polynomial. And it's a polynomial with no constant term. So it's if I divide by x, it's OK. And what it turns out to be when I take the trace and I divide by x is I get this polynomial here. Just trust me. And now I can check. It's quite easy to check that this polynomial, now that I've produced it, has all of the properties that I want. So I'm going to say that the ith dual code word ci is going to correspond to the ith polynomial here. So first I need to show that this is indeed a dual code word. So that means for Reed-Solomon codes that the degree should have degree at most n minus k. In this case, n minus k is just n over 2 because k is n over 2. N is 2 to the t, so n over 2 is 2 to the t minus 1. So I want degree strictly less than 2 to the t minus 1. And I can go up here and see, aha, indeed the degree is strictly less than 2 to the t minus 1. It's in fact 2 to the t minus 1 minus 1. So we're good there. The next thing I want to check is that I get full rank sort of here. So if I plug in 0, the symbols I get should have full rank. And I can see, again, just by looking at the formula, that if I plug in 0, the things I get are just the gamma i's, which necessarily have full rank because I define them to be a basis. So good. And then finally, the last thing is that for any other alpha that's not equal to 0, if I plug in that non-zero alpha into any one of these GIs, I get something that just has rank 1 as I varies. And to see that, we can just look at this version of the expression. So remember, trace is something that takes in an element of the big field and spits out just a bit in an element of the small field. And so what this thing is equal to is just 0 or 1 divided by alpha. And so whether or not it's 0 or 1 depends on I, but nothing else depends on I. So this whole thing, this row, is just a bunch of zeros or 1 over alphas. And so it has rank 1. And that's it. So that's the whole construction, is I prove to you that I need to find some nice low-degree polynomials, and then I pull these ones out of a hat. And the punchline that you get for these ones in particular is that for full-length rate 1/2 codes over f2 to the t, you can repair one failure by just, whoops, oh no, go back. Sorry, there we go. By downloading just 1 bit from every surviving node. And that 1 bit is coming from the fact that these other rows all had rank 1. And this construction you can generalize a bit to get high-ranked codes as well. So does this make sense to the questions?
Yes.
Cool. Yeah. So this is a construction, and it turns out to be optimal for Reed-Solomon codes in this parameter regime. And while we're on the subject of a single failure, I just want to sort of give another punchline, which is not due to me, from Tomo, Yang, and Barg, as a stock paper in 2017 in the high subpacketization regime. And they show that Reed-Solomon codes can exactly achieve the cut set bound. They need to take t quite large, which they also show is necessary. And they managed to get the bandwidth to be sort of this nice expression that we saw before. And again, their result goes by choosing a different family of really nice polynomials, and also choosing the evaluation points really carefully. So it's a much more complicated construction than the one I showed you, but it can get this really strong bound. So it's a beautiful paper. I would recommend it. Cool. Okay, so I just like really misjudged time. So now I'm like a little bit through. So that was sort of the story of the single failure case. Maybe I'll just like very briefly wave my hands about what can happen for the multiple failures case. So we might like to extend what happened to single failures to multiple failures. So what happens if 2 things fail or 3? So for motivation, I said at the beginning, 98% of the time, 1 failure happens, but sometimes multiple failures do happen. And also it might be that multiple failures would happen more often if we could handle them well by doing some sort of lazy repair. And additionally, I just think it's kind of a nice question, especially if we do manage to find other applications for this nice polynomial interpolation problem. And so for all these reasons, we might want to study like what happens if there's more than 1 failure. There's a couple of different models that we can use to think about this here, right? So in just this picture, like how it's not exactly clear how we should measure bandwidth anymore. Do I measure like all of the communication that goes on between all of the nodes? Do I measure communication just from the surviving nodes up here to sort of the joint surviving nodes down here? There's a few different models. The one I'm going to talk about is called the centralized model, where sort of I'm going to count I'm going to imagine there's some sort of centralized repair center, which is in charge of repairing all the failed nodes. And I'm going to count bandwidth from the surviving nodes to the repair center, but I'm not going to count any bandwidth within the repair center. So this model has been reasonably well studied in the regenerating codes literature. It's not the only interesting model. There are other models, for example, the cooperative model, which does sort of take into account communication that goes on within the repair center. But I'm going to focus on just this one for now. And again, there's been a little bit of work for scalar MDS codes and for Reed-Solomon codes in particular in this area, especially in the past few years. So very recently, Ye and Burak showed that you can actually meet the cut set bound for multiple failures. So there's a version of the cut set bound for multiple failures, and they showed that Reed-Solomon codes can meet it, which is super cool. Again, this requires really large subpacketization. If you want to look in the small subpacketization regime, much less is known. So there's this recent paper by Dow et al. Where they give a non-trivial repair scheme for 2 or 3 failures. And then there's a work, which I'm just going to briefly mention now with myself, which is joint with Jay Mardia and Burak Bartan, who are PhD students at Stanford, about how to sort of generalize both the work of Dow et al. And the work on the single failure case that I already told you about for our failures. And once again, this is going to go by a very similar framework to what we saw before. Basically, nice properties of the dual code is going to apply nice multiple failure centralized schemes. And so I'm not going to go through the whole details again, but the basic picture is really the same. So before I said, what was my nice property? I want a set of 2t, or before I wanted a set of t code words for every single I that might fail. Now, suppose there are just 2 failures for every single I and j that might fail. Instead of wanting t code words, I want 2 t code words. And I want them to have the property so that if I look at the rows indexed by I and j, those guys should be full rank. And here, the sense of full rank is that I'm going to take all of these different field elements, I'm going to treat them all as little tiny vectors, stack them together, and demand that the resulting matrix has full rank. And then similarly, for all the other rows, I'm going to want those to be low rank, just the same. And the generalization for R failures is that I'm going to want RT code words so that the appropriate set of R rows corresponds to a RT by RT full rank matrix. All the other rows have low rank. And the proof that this implies a repair scheme for multiple failures is very similar to the one that I just showed you. Yeah, basically the idea is that the full rank parts give you all the information you need, and then the low rank parts, and you can get that information from the low rank parts, which means you can do it with low bandwidth. And once again, we get a corollary for Reed-Solomon codes, which says that nice low-degree polynomials imply nice multiple failure centralized repair schemes. And we can find some nice low-degree polynomials. So I'm just going to flash by this screen in the interest of time. But basically, we can generalize the polynomials that we came up with before, those GIs. We can generalize them to multiple failures just by making them a little bit fancier. So has the same basic form. I've just made what shows up here a little bit fancier. And we can check that this satisfies the requirements that we need. And the punchline here, so this one I will spend more time on, is that in exactly the same setting that we had before, so full length rate 1/2 codes over f2 to the t, and now for R, which is the number of failures possibly larger than 1, this gives non-trivial results all the way up to root n or so. We can repair these R missing nodes using roughly this many bits from every surviving node. So remember, for R equals 1, we just got 1 bit for every surviving node in this particular parameter regime. And you can check that when you plug in R equals 1 here, indeed, you get 1. 1 plus log base 2 of 2 minus 1, which is 0, is 1. And this sort of gives a generalization of that. So this, as R gets bigger, like the number of nodes you need, or the number of bits you need to download from each surviving node increases, but it increases sort of gracefully up until you get hit about R equals root n, when this becomes equal to the trivial scheme. And again, we can generalize this to get high rate codes also. OK, so sorry, I kind of blew by that second bit just in the interest of time. But are there any quick questions about the multiple failure setup?
I think no questions.
Okay, cool. Yeah, so again, it's the framework is pretty much the same as in the single failure case, but it turns out to be a bit trickier to come up with these polynomials. Great. Okay, so now we've sort of finished the sub-outline. So sub-outline, small part of the big outline. So now, only 15 minutes late, maybe I can sort of do my official recap and end with some open questions. So let me just recap briefly. So what is the point of the talk? So this is similar to the slide I had at the beginning. So the point of the talk was that regenerating codes are codes which admit low bandwidth repair of just a few failures. And also that codes we know and love, like Reed-Solomon codes, are actually pretty good at this, which for me, when I first learned about this, I found very counterintuitive because it feels like the array code thing is very important for making regenerating codes. But it turns out it's not. Just Reed-Solomon codes themselves are pretty good at it. And in this talk, I gave just an overview of recent work in this area, which says that, and the punchlines are that linear repair schemes for scalar MDS codes are characterized by this nice algebraic property of the dual code. Also true for multiple failures. And this means that by coming up with nice bunches of dual code words, which in the case of Reed-Solomon codes means just nice polynomials, we can come up with repair schemes for Reed-Solomon codes and any scalar MDS code we like. Cool. So I'd like to conclude with some open questions, because I think that there's lots of really interesting directions. So one question which I'm interested in, actually both for scalar MDS codes and for general regenerating codes, is what's the best bandwidth we can get in the low subpacketization regime? So this high subpacketization regime, sort of meeting the cut-set bound, has really been studied quite a bit in regenerating codes. And now for scalar MDS codes, thanks to the work of Tom Oye and Barg, we now know that at least Reed-Solomon codes can do this as well. But in the low subpacketization regime, much less is known. So we have a tight lower bound for the one failure case if we assume linearity. But if we don't assume linearity, we don't know if our bounds are tight. There's a lot of open questions there. On the note of linearity, another question, in both the low subpacketization and the high subpacketization regimes, are what can nonlinearity buy you? So basically all our schemes, all the schemes that I presented and on all the known schemes for Reed-Solomon codes are linear. And all the lower bounds are also hold only for linear codes. So it might be possible to do much, much better with a nonlinear scheme. And I just have no idea how to approach this question. I think it's a very interesting question. Yeah, this was asked to me recently by Zaki Tamo, so I think it's a very nice question.
But what is meant by nonlinear, right? So because you have multiple fields, so something that is
nonlinear over the small field. So basically, everything that I told you, like all the schemes, were taking these traces, which is basically doing stuff that's linear over the small field. But you could imagine doing something like, instead of saying that a node should return the trace of something times its contents, it could just return anything it wants, any function it wants of its contents. Possibly nonlinear over the small field.
We did trace over, like, I don't know if I'm saying something that makes sense, but something in the intermediate field would be linear, or I don't know. Like,
that would be even more linear, trace over an intermediate field. Yeah, so here, this would mean like just getting away from the trace framework. So instead of thinking about a trace, which is like an inherently linear object, thinking about like, okay, if my contents are 0, 0, 1, return 1. If my contents are 0, 1, 0, return 0. Yeah, or like I can, arbitrary truth tables are allowed. What can I do? And yeah, I have no idea either how to start. Yeah, how to start thinking about this. I think it's a really nice question. Yeah, another question which I completely didn't talk about at all is what the nodes are actually doing during the repair process. So what the nodes are doing in the scheme that I presented to you is they're basically just looking at their contents as a vector and taking the inner product of that vector with some other vector and returning the resulting bit. This is pretty efficient in the sense that doing linear operations is pretty efficient, but they still do need to contact like a constant fraction of the nodes on every single of the bits on every single node. And you might try to minimize the amount of disk access that's actually done on the node's part. There's been some recent work on this by Dow et al. In the context of Reed-Solomon codes. but there's tons, again, that's open in this area. And then finally, the question that I'm most interested in, that I really want to leave you guys with, is where else is this approach useful? So I think Salim asked this towards the beginning of the talk. Like Reed-Solomon codes show up all over the place. And what I've shown you here is that there's been a bunch of work in the past few years working on how do we do polynomial interpolation in a communication efficient manner. And this seems like a much more general question than distributed storage. In particular, crypto seems like an actual application area, like secret sharing, multi-party computation, stuff like that. And also applications in maybe coded or distributed computation, which are a little closer to the distributed storage setting. So I'd love to see more applications of this stuff. So I'm super happy to talk to anybody later who has any ideas of where this might be useful. Okay, so I'll finally wrap up now. So thanks very much. I'll have to take more questions.
Thank you, Mary. This was very interesting. One immediate kind of remark, do you know if this has been, or it could be readily applied to, for example, MRD codes? Because they look a lot like, meaning Gabrielin codes, they look a lot like Reed-Solomon, right?
Oh, I see.
Or does it, I mean, is the question interesting?
Yeah, or the question makes sense. Yeah, I think it's interesting. Right, so the question is like for rank distance codes and for rank metric codes?
Yes, yes.
Okay. Yeah, I don't know too much about those codes, actually. I don't see any reason a priori why you could not do something similar, but I have not tried. I think it's a really nice question.
Okay. So if there's no more questions, so
can I make a quick remark? So yeah, just coincidentally, so I talked to Ivan about this same question after the work, that if it can be extended for rank metric codes. Yeah, they were trying on that, but it looks like interesting question.
Okay, cool.
So, yeah, so Ivan thinks it's interesting and not so trivial, so it may be interesting.
Okay, awesome. Well, I mean, if he thinks it's interesting, then it's interesting.
And one other quick question. So this with regards to just more of a speculate. I mean, I wanted to know what you think about if we deviate from the model where you essentially repair from any D to more like what Salim had done with those table-based type of repairs. Do you think it might have some impact on subpacketization? Or?
That's a really good question. Yeah, so I guess in this work, I was mostly talking about the case where D equals n-1, so the distinction between any D and exists at D doesn't make too much of a difference. Yeah, I'm actually really curious. So I don't. This might just be my ignorance. I'm not sure of. Actually, probably Salim, you know much better than I do. What exactly can be done? Like, could we even possibly go beyond the cut set bound or something if we get any D?
Yeah, I mean, when you have a table, tricky. Sometimes you can do much better than the bound.
Yeah. So yeah, I'm not too familiar with that work sort of in the regenerating code space.
I see.
But yeah, I think actually I think that is a really interesting question of whether or not one can get results sort of similar to the ones that Tamuye and Bard got for Reed-Solomon codes, but with lower subpacketization by not demanding that all sets of D nodes be repaired. Yeah, I think that's a really interesting question. I have no intuition about what the answer is, but
sure. Yeah, thanks.
Yeah, that's really nice.
One more question, maybe the last question.
Yeah.
So in many cases, I mean, I'm trying to think from a more engineering perspective. Like, I may have a system that's already using a specific Reed-Solomon, so I don't want to change the code. Would you be able to, or I mean, have people studied this? Like the code is fixed, then what is the best I can do with that code?
Yeah, that's also a great question. I thought about that a little bit. So in this paper with Venkat that I cited from a few years back, we looked at the specific code that the Facebook warehouse cluster was using, because at the time their code was all open source. So you could go and actually look at what Reed-Solomon code they were using. So they were using some like 1014 code with like these particular evaluation points. And so we took a look at that set of particular evaluation points and basically did what pretty much amounted to a brute force search to find a good scheme. And I believe since then there's been some more work being a little bit smarter about it, which can come up with some better schemes. To the best of my knowledge, I don't know of an efficient algorithm that will take, you give me some evaluation points and I tell you a good recovery scheme. Although the last I looked for such an algorithm was maybe a year or two ago. So it's possible that someone has come up with one. But as of a year or two ago, I think that that's a really interesting question to come up with like an efficient algorithm, which will say, you give me a code, I give you a repair scheme.
Yeah.
Yeah.
All right. So thanks a lot, Mary. This was very interesting.
Cool. Yeah, and thanks so much for the invitation. This is fun. And so sorry for going so egregiously over. I guess the advantage of the internet talk is I can't see people walking out.
No, I guarantee you, everyone is still here.
Okay. Great.
Okay. All right. Thanks a lot.
Awesome. Well, thank you so much.
Yeah.
Bye.
Thank you.